I'm Brandon, third year PhD student at the University of Surrey. So today I'll be talking about a machine learning model for predicting the creep response in similar nuclear reaction joints. So firstly, I'll talk about why the project's important in terms of nuclear fusion, and then talk about the fusion environment itself. So then I'll talk about the method, so the data set generation, the algorithms I decided to use, and then the optimization of the hyperparameters and how you deal with the data set you've created, so feature screening. And then I'll talk about a bit about the results in terms of hyperparameter optimization and algorithm comparison, and then conclusion and further work. So again, why is nuclear fusion important? Well, there's obviously an increase in energy demand every year. And with the rising populations, this is going to increase further. So fossil fuels are still accounting for quite a lot of the worldwide generation. Obviously, this then leads to increased CO2 concentrations in the air. So this increases the amount of pollutants in the air, drives the energy crisis, increases higher mortality rates, and increases in disease. So nuclear fusion is thought to have the potential to offer a sustainable and clean energy, allowing a shift from these traditional schemes. So, as been mentioned before, the fusion reactions creates an extremely hard working environment, bringing about a lot of challenges for engineering materials. So my work is focused on Urethane 97, which is a specialist material currently being developed. Urethane is good. It's part of the RAFAM steel group, so reduced activation. So when it's irradiated, you can just bury it underground for 100 years, as opposed to 1,000, but it still has high temperature strength that austenite steels would. So laser welding then has been picked as the most appropriate mechanism for assembly and investment maintenance. This because the deep penetration it allows and the relatively small thermal history it will develop in the material. But obviously welding will create quite a complex microstructure. So where the two materials are melted and solidified, that's your fusion zone. In this zone as well, precipitates completely dissolve into the matrix. And then you have your heat affected zone where melting doesn't occur, but you still exceed temperatures that allow phase transformations of the initially stable microstructure to occur. And then you'll have your base material, which is thought to be unaffected. So the operating temperature for this structural steel is 350 to 500. So why creep is important is for a given stress at the lower end of that temperature range, it doesn't matter that much. But towards 500, the dislocations can start climbing over the precipitates, which can lead to plastic deformation. So for the data set, at the moment, it's focused on as received UFO, not welding. So data is quite sparse, but I was lucky to find a reference which gave me the temperature history of different UFO samples, the test stress, stress temperature, and then it gave the tensile properties as well, yield stress and UTS, and then gave me the creep lifetime. JMAT Pro has then been used to get the temperature-dependent material properties, as you can see there, and how the ferrite and pearlite microstructure changes in these temperatures. So as we've seen there, so these input features were then put into these different machine learning algorithms to then get the target feature, which in this case is the creep lifetime. So the different algorithms are used are the artificial neural network, random forest regression, and partial least squares regression. So why these are used is because the ANN, if you think about it, is your staple algorithm used. But an issue with the ANN is it's very prone to overfitting. So I was using that as a baseline to assess the data set that I had created and see if it was sufficient enough. Random forest regression then is quite known to not have overfitting due to the random and ensemble approach it takes with the input data. And then partial least squares regression is good because it takes two uncorrelated bits of the input and finds the maximum difference in the output. So it can be used to reduce the data set down to its actual important components. So hyperparameter optimization then, and how you deal with the input data is fairly important. So for the ANN, the hyperparameters are the number of layers, the number of nodes per layer, and then the activation function that acts over the layer. For random forest regression, it's the number of trees, so how the data is split, and then the max depth of the trees. For the least regression, it's the number of latent variables, which is the number of variables selected to represent the outputs, as I said before. So how are these optimized? For the ANN, there's luckily inbuilt in Python libraries, Keras tuner. Similarly for the RFR, schematic ops tuner. For the least regression, I just did it manually because it's just one. And it can only be between 1 and the amount of inputs you have. So it's between 1 and 13. So it's just easy. So for every algorithm, the data was split 70% training, 15% validation, 50% test. So the training was used to train obviously train the algorithm. The validation was used to assess how the optimization scheme worked. And then it can go back if it didn't meet a certain threshold. And then the test is what's actually used and will be shown later for actual prediction because it's unseen during the training process. So to work out what variables to use for the latent variables, Pearson's correlation coefficient is used, as you can see there. So then you can find between each variable which one the lower ones that you will use to predict the biggest output in the variables. So the results of this are for the ANN, how Keras tuners works is it tries to find the lowest validation loss. So you find the local minimum in a hyperparameter space you can create. So from this, the number of layers is 3, and then 42 average nodes per layer with a Rayleigh activation function. RFR is similar, but instead it tries to maximize the R² score. So then you try and find the local maximum in that hyperparameter space, which leads to 206 trees and 252 max depth. So for the least regression, as I say, I did it manually. So from that, I just found 10 was the best. I can go up to 13, but if I did that, the R² went extremely negative, so you couldn't even see that part of the graph. So 10 is definitely the best. So for the algorithm comparison, as I thought, the ANN performs badly with an R² of 0.5. And then the other two, so random forest is 0.81 approximately, and then 0.8 for random regression, least squares. But as you can see from all of them, they perform extremely poorly at the early lifetime. And that, given that with the comparison of the results for the ANN, leads me to believe, obviously, there needs to be more data fundamentally. Because then the partial least squares is actually predicting a negative lifetime at this point, which is nonsensical. So to conclude, yeah, data set has been generated to predict correct lifetime based on a E97 heat treatment. Hyperparameter optimizations has been successfully implemented. Good performance for the random forest regression and the partial least squares, worse performance for the ANN. So as I say, the results show that the model struggles to learn the relationship at lower creep life. So from this, what I want to do is actually extend it to the Wildman. So to do, I'm going to use EBSD data that Bin has obtained previously to characterize the microstructure across the world. So you've got your kernel average misorientation, which is thought to be linked to dislocation density. You've got your prior austenite grains, which help dictate where the martensite packets will be, and then just general grain size on the end. So yeah, thank you for listening. Are there any questions?